In this video, we are going to be reviewing Module 7 from Statway. Now remember where we left off. In Module 6, we learned about the z-score. The z-score, once again, is the number of standard deviations a data value is from the mean. And we learned that a data value is considered unusual if it's 2 or more standard deviations away from the mean. We also learned how to get the area under a curve using normal CDF. Now, Module 7 is a bridge from Module 6 into Module 8, where we're going to be doing confidence intervals and hypothesis testing. In Module 7, we do a little bit of constructing confidence intervals. The purpose of a confidence interval is to estimate the true population proportion, P, using the sample proportion, P hat. Now, in real life, it is rare that we're going to know the value of P. We're trying to estimate the value of P, the true population proportion, and we normally do that by getting a sample and computing P hat. Now, there are a couple of terms we should know. When we're dealing with the population, the proportion is referred to as a parameter. When we're dealing with the sample, the proportion is referred to as a statistic. So we have population parameter, sample statistic, or as I show my class, PPSS. Population parameter, sample statistic. And of course the joke I always throw in is that I have two poodles, and when I take them for a walk and I'm always telling them PP, that always reminds me of Statway. Okay, as the sample size increases, as you take more and more elements in your sample, whether it's people or M&Ms, the margin of error decreases as the sample size increases. In other words, you get more precision in your interval. It's more precise. Precise means the interval is narrower. That's a good thing. If you have a wider confidence interval, that's bad. You have less precision in your estimate. And again, to re-emphasize, we are trying to estimate the population proportion P using the sample proportion P hat. Now, where would you get more variability in your sample data? Well, if you have a small sample size, then you're going to have more potential variability in your P hat values. When you have a larger sample size, you're going to tend to have less variability in your P hat values. So for example, if M&M's was advertising that 25% of its candies are blue, where would you expect to see more variability in the P hat values for blue candies? In a bag that has 10 pieces? Or a bag that has 100 pieces? It would be the bag that has 10 pieces. There you're more likely to get a wider variation in your P hat values. Now, every time you create a sample, each sample has different sample proportions just due to chance variation. Remember, there's variability. And most of the time, your P hat values that you're getting from your sample are going to be different than the true population proportion. Now, if you were to construct a dot plot using a computer simulation of all possible P hat values, the mean of all the possible P hat values, in other words, the center of the dot plot, is just equal to the true population proportion. Okay, right over here. Okay, so again, the true population proportion is the mean of the p hats. And the standard deviation of the p hats is the square root of p, 1 minus p over n. Now, you're going to need the standard deviation later on in order to get a margin of error for your confidence interval. P is the population proportion and n is the sample size. For a 95% confidence interval, we're going to use the empirical rule. Now, 95 is not the only type of confidence interval. The other main ones are 90% and 99%. But you're going to see that the value of 2 here is from the empirical rule, and that states that roughly 95% of your data is within 2 standard deviations of the mean. So, the margin of error is roughly 2 standard deviations, 2 times the square root of p 1 minus p over n. How do you construct a confidence interval? Well, if we're going to estimate p, you take p hat plus or minus the margin of error. So for example, suppose we had a p hat value of 0.45. That's your sample proportion. And suppose the margin of error was 0.02. How would we get the confidence interval? You take your p hat of 0.45 minus the 0.02. That brings us to the 0.43. And your 0.45 plus the 0.02 brings us to 0.47. What is a 95% confidence interval? What does it mean? Well, there are 2 interpretations to it. One is we're 95% confident that the true value of p lies in the interval. Another interpretation, if we were to create sample after sample after sample, and each of those samples would have a slightly different p hat value, so we would get slightly different confidence intervals. 95% of these confidence intervals would contain the true value of p. 5% of the intervals would not contain the true value of p. Now, another thing is we want the sampling distributions of the sample proportions to be approximately normal, so we can construct our confidence interval. Now, there are 2 conditions that have to be met. N times p has to be bigger than or equal to 10, and n times 1 minus p has to be bigger than or equal to 10. And finally, in Module 7, the z-value is your data value p hat minus the mean. What is the mean of the p hats? P over the standard deviation. So that's your formula to get the z. Okay. Now, let's look at an application here. In the November 2008 election, Barack Obama received 51% of the votes cast in Florida. Many news organizations conduct surveys before elections to try to predict the winner. Suppose pollsters conducted a survey of a random sample of 600 likely voters in Florida shortly before the election. If a survey was conducted very close to the election, we can assume the true proportion of the population who planned to vote for Obama at that time was 51%. Now again, we're making an assumption about P. Normally we can't do that. But in Module 7, this is a transition to Module 8, so we can make an assumption. So we're assuming that p-value is 0.51. Okay, now suppose they ran their survey. So this is the sample. 321 of the 600 people said they planned to vote for Obama. So what is your p-hat, your sample proportion? So your p-hat is 0.535. What is the standard deviation? Now, if we can assume that we know the true value of p, which we normally wouldn't, but if we do know it, then it's the square root of p, which is 0.51, not the 0.535. That's the p-hat. the square root of p, 1 minus p, that's where the 0.49 comes from, over n, 600. So the standard error, which is another word for standard deviation in a sample, is 0.0204. What is the margin of error? Well, the margin of error is 2 times the standard deviation. So 2 times that 0.0204, which gives us to 3 decimal places a margin of error of 0.041. Now, how do we get a confidence interval here? We take not the p-value, the p-hat value, 0.535, plus or minus the margin of error, 0.041. So again, 0.535 plus or minus 0.041. And that's our confidence interval there. So we are 95% confident that the true proportion of people in Florida who will vote for Obama or would vote for Obama back in 2008 is between 49.4 and 57.6%. Now, what if we ask the question, do we think that the number of the percentage of people that would vote for Obama, could that be as low as 48%? Probably not. 48%, 0.48, is not in that interval. Okay, let's look at another example here. In 2011, Gallup conducted another poll asking people how they felt about income inequality in the U.S. This time, 45% of the 1,012 adults surveyed believe that income inequality in the U.S. is a problem that needs to be fixed. When we compare the percentages in the 2 poll results, it appears that in 2011, fewer people were concerned about income inequality being a problem. We want to know, is this really true? So we're going to test the claim that the proportion of all adults in the U.S. who believe income inequality is a problem was less than 52% in 2011. So again, this is a bridge into Module 8 for hypothesis testing. Okay, so look at the sample proportion for 2011. Can you determine whether the proportion of those who believe income inequality is a problem has decreased? No. Although the sample proportion is lower than 0.52, the difference just could be due to variability. We know there's going to be variation every time you run a poll. So the first thing is, let us get the standard deviation. Now remember, the mean of the p-hats is the assumed p-value of 0.52. So you do p, 1 minus p, over n, 0.016. Is normality satisfied? Yes, NP is 1,012 times 0.52. That's bigger than or equal to 10. And 1 minus p, bigger than or equal to 10. Now, how do we get the z-value? It is the p-hat value, 0.45. That is from the 2012 poll. Minus p, the assumed p-value of 0.52, over the standard deviation. Minus 4.38. Now, first of all, minus 4.38. That is a very, very large z-value in absolute value. That is over 4 standard deviations from the mean. That is quite unusual. So if the true population proportion was really still 0.52, getting a 0.45 would have been highly unlikely. What is the probability we would have gotten a 0.45 or less? That's the probability z is less than or equal to minus 4.38. On your TI, you would do normal CDF, comma. Now this is a tail to the left. So you would have normal CDF minus 1E99, comma, minus 4.38, which is 6 times 10 to the minus 6. That's almost 0. So if the true population proportion was 0.52, it is almost impossible we would have gotten a sample statistic of 0.45. So This is leading up to hypothesis testing, but again, the sample proportion of 0.45